Hello everybody, my name's Iman. Welcome back to my YouTube channel. Today we're going to be discussing the electronic structure of atoms, and we're going to cover the following objectives. The first objective is titled electromagnetic radiation. We're going to begin by learning about waves and their three characteristics: wavelength, frequency, and speed. And we're also going to cover the electromagnetic spectrum and understand its significance. Then the second objective is titled The Nature of Matter. Here we're going to discuss how electromagnetic radiation isn't emitted continuously, but in discrete packets called quanta. And to clarify this concept, we're going to dive into three key experiments: blackbody radiation, the photoelectric effect, and the double slit experiment. Then we'll move into the third objective, the atomic spectrum of hydrogen. Here we're going to talk about the absorption and emission spectrum of hydrogen, and we're also going to highlight the importance of hydrogen's line spectrum and what it reveals about atomic structure. Then we move on to the fourth objective, Bohr's model of the hydrogen atom. With the line spectrum fresh in our minds, we're going to explore Bohr's model of hydrogen, and we're also going to cover the Rydberg equation, which is crucial for understanding energy levels. Then we'll move into the fifth objective. We're going to discuss here how Bohr's model, while fitting hydrogen's energy levels, is fundamentally flawed. Instead, we'll introduce quantum mechanics, we'll talk about orbitals, Heisenberg's uncertainty principle, and that will lead us into our discussion on quantum numbers, which is our sixth objective. Here we'll break down the four quantum numbers: principal, angular momentum, magnetic, and spin. And then finally, our seventh objective is where we will wrap up with an explanation of electron configuration. With that introduction, let's go ahead and get started with this first objective. Here we're going to consider the properties of light, more properly called electromagnetic radiation. Now, one of the ways that energy travels through space is by electromagnetic radiation. The light from the sun, the energy that's used to heat up your food in the microwave, the X-rays that are used by your doctors and dentists, these are all examples of electromagnetic radiation. And although these forms of radiant energy seem quite different, they all exhibit the same type of wave-like behavior, and they travel at the speed of light in a vacuum. Now, waves actually have three primary characteristics: wavelength, denoted by lambda; frequency, denoted by this Greek letter nu; and then speed. Wavelength is the distance between two consecutive peaks or troughs in a wave. Then frequency, this is defined as the number of waves or cycles per second that pass a given point in space. And then as for speed, all types of electromagnetic radiation travel at the speed of light. And the speed of light is equal to 2.998 times 10 to the power 8 meters per second. Now, there's an important consequence for this. This means that longer wavelengths result in low frequency and shorter wavelengths result in high frequency. And so therefore, there is a relationship between frequency and wavelength. And the relationship between frequency and wavelength for electromagnetic radiation is going to be the following: C, which is the speed of light, is equal to lambda, which is wavelength, multiplied by nu, which is frequency. Now, taking this into consideration, all right, and now that we understand the relationship between wavelength and frequency, let's dive into electromagnetic radiation itself. Electromagnetic radiation includes a broad range of waves, from radio waves to gamma rays. These different types of waves form what we call the electromagnetic spectrum. And the spectrum is classified based on wavelength or frequency, with each category of radiation possessing unique properties and applications. Now, radio waves have the longest wavelengths and the lowest frequencies, while gamma rays actually have the shortest wavelengths and the highest frequencies. In between these, we can have microwaves, infrared radiation, visible light, ultraviolet radiation, and X-rays. And these categories, they vary in energy as well, which affects how they interact with matter. We're going to cover how frequency and wavelength are related to energy here in just a little bit. But a crucial characteristic of electromagnetic radiation is that it consists of two oscillating fields, an electric field and a magnetic field. And these fields are perpendicular to each other and to the direction of the wave travel. Now, this can get and become a complicated topic, but we're going to keep it pretty simple for what we need to know for this particular chapter. What we need to know is that electricity and magnetism are essentially two aspects of the same thing. Changing the electric field creates a magnetic field and vice versa. Now, the interactions of these fields allow electromagnetic radiation to propagate through space and interact with charged particles. So for example, visible light, it falls in the middle of the spectrum. It enables things like vision and photosynthesis by interacting with atoms and molecules. And in contrast, high energy gamma rays, these can ionize atoms, leading to their use in sterilization and medical imaging. Now, unlike waves, electromagnetic radiation is not emitted in a continuous manner, but instead it is emitted in separate packets or bundles called quanta. And this will be the goal of Objective 2. The second objective is titled The Nature of Matter, and here we want to talk a little bit about history. It's probably fair to say that by the end of the 19th century, physicists were feeling rather smug. They thought that they had everything figured out. And one idea that was really common during this time was that matter and energy were distinct. Matter was thought to consist of particles, whereas energy in the form of light was described as a wave. Particles were things that had mass and whose position in space could be specified, and waves were described as massless and delocalized. Their position in space could not be specified. It was also assumed that there was no intermingling of matter and light. And this idea was so wrong. And it was through a couple of important experiments and discoveries made in the 1900s that everything changed and the era of modern physics and quantum mechanics began. So here we're going to talk about a couple of experiments, and there's going to be a lot of details and history and background, but I want you to remember that the main takeaway here is that matter and energy are very much related. So let's go ahead and get started first with a discussion on black body radiation. Black body radiation is the electromagnetic radiation emitted by an idealized object that absorbs all incoming light. In classical physics, the theory predicted that radiation intensity should increase indefinitely at shorter wavelengths, which would result in an infinite amount of energy. And that just wasn't right. So Max Planck, he decided to tackle this issue by studying the radiation patterns that were emitted by solid objects heated to incandescence. And he found that classical theories really couldn't explain the results because they assumed that matter could absorb or emit any quantity of energy. And this led to some very wrong conclusions. To address this inconsistency, Planck proposed that energy could be gained or lost only in discrete whole number multiples of a fundamental unit, which he defined as h nu, where h was Planck's constant and nu was frequency. Planck's constant is equal to 6.626 times 10 to the minus 34 power joules per second. And so the energy change in the system can be said to equal Planck's constant multiplied by frequency. And so this equation directly linked energy to frequency, and it was further related to the speed of light equation. So we talked about earlier how the speed of light is equal to wavelength multiplied by frequency. If we rearrange things to solve for frequency, we would get that frequency is equal to light over wavelength. And if we replaced frequency with this definition, now we have a relationship between energy and wavelength. All right, so there is a relationship between energy and frequency and between energy and wavelength. And this reinforces something that we covered earlier. Shorter wavelengths have higher frequencies and thus carry higher energy. Now, Planck's proposal, it was surprising because it contradicted the classical assumption that energy is continuous, meaning it could be transferred in any amount. Instead, he showed that energy is quantized and it's transferred in discrete units called quanta. And this discovery indicated that energy itself has particulate properties, which fundamentally changed our understanding of physics, and it led to the development of quantum mechanics. Now, the next experiment we want to talk about is the photoelectric effect. The photoelectric effect is a phenomenon where electrons are ejected from a metal surface when struck by light of a certain frequency. Albert Einstein's analysis of this effect revealed a couple of important things. First, he observed that if the frequency of light is below a certain threshold, which he called the threshold frequency, no electrons are emitted regardless of the light's intensity. And so what that meant was that simply increasing the brightness of the light is not going to cause electrons to be emitted if the frequency is too low. But then when the frequency of the light exceeds that of the threshold frequency, then electrons are emitted, and their number actually increases with higher light intensity. In addition, the kinetic energy of that emitted electrons also rises with increasing light frequency above that threshold, meaning the electrons are ejected at higher speeds. Now, Einstein explained these observations by proposing that light consists of discrete particles called photons, and each photon carries a fixed amount of energy that's proportional to its frequency, and that's given by the formula we saw earlier. Energy is equal to Planck's constant multiplied by frequency. The energy required to eject an electron from that metal surface, this is known as the work function, and this corresponds to a specific minimum frequency called the threshold frequency. Now we can take those ideas, all right, and reaffirm them using a mathematical equation. This expression says that the kinetic energy of the electron and kinetic energy is equal to 1/2 mv squared. That is equal to the energy of the incident photon coming in to hit the metal surface minus the energy that's required to remove an electron from the metal surface. So in short, the point is, if the frequency of the photon hitting the metal surface is enough to emit an electron, then that electron will be emitted. And then any frequency higher than that will just correlate to that electron being emitted with more kinetic energy. If the frequency of the light that's hitting the metal doesn't meet that threshold frequency, then no electrons will be emitted. And this equation shows that only photons with a frequency higher than the threshold frequency actually have enough energy to overcome the work function and release electrons. And like I said earlier, any extra energy above that work function is just converted to the kinetic energy of that emitted electron. Now, in a related development, and we don't want to get into this too much, but in a related development, Einstein's special theory of relativity, it introduced his famous equation E equals mc squared. E is energy, m is mass, c is the speed of light. And this equation indicated that energy itself has mass. And we can rearrange this calculation, this equation, and we can write something that says that mass is equal to energy over the speed of light squared. And so this shows that it's possible to calculate the mass associated with a given quantity of energy. So for instance, the mass of a photon can be calculated using its energy expression, which is dependent on wavelength. Now, the main point here is, and be very careful, photons, they have no rest mass, but they do exhibit mass in a relativistic sense. And we can take this expression, by the way, and because we know E equals Planck's constant times speed of light over wavelength, we can replace E with that expression and again, see that there's a relationship between mass and wavelength. And again, does a photon have mass? It doesn't have rest mass, but it has relativistic mass. Now, from the work of Planck and Einstein, we can draw several significant conclusions. One, energy is quantized. This is the point that I want you to take away from all of this. Energy is quantized and it occurs only in discrete units called quanta. Second, electromagnetic radiation, once thought to be purely wave-like, now shows characteristics of particles as well. And this is a phenomena that's referred to as the dual nature of light, or wave-particle duality. Now, this work raises an intriguing question. Can matter itself exhibit wave properties? This was a question that was tackled by Louis de Broglie, he's a French physicist, and he explored this concept in the early 1920s, and he developed the equation that allows us to calculate the wavelength of any particle. And so this is that equation right here. Now, so far, the important equations to take away is this de Broglie equation right here that relates wavelength to mass, frequency, and Planck's constant. And then this equation right here as well, which relates energy to frequency and it also relates energy to wavelength. These are the two important equations that you should definitely commit to memory. Now, let's move on to that third and final experiment that we want to talk about here in this second objective. We now understand that light and other subatomic particles, they can exhibit both wave-like and particle-like properties. This is a phenomenon known as wave-particle duality, and it was further confirmed by the double slit experiment. Now, this experiment can get really tricky and complicated, but we're going to try to keep it as short and precise and to the point as possible. In this experiment, light is directed through two parallel slits onto a screen. As the light passes through the slits, it diffracts or bends around the edges and it spreads out. And then those diffracted waves, they can overlap and then they can interfere with one another. And that will produce an interference pattern on the screen that's composed of alternating bright and dark bands. The bright bands results from the constructive interference where the waves actually reinforce each other, and the dark bands are due to destructive interference where the waves cancel each other out. This interference pattern, that provides clear evidence of the wave-like behavior of light. Then later in the 20th century, scientists actually repeated this experiment, but with electrons this time. If electrons only behaved as particles, then they would pass through the slits and then form two distinct spots on the screen, and that's it. But instead, the electrons created the same interference pattern that was seen with light, demonstrating that they also behave like waves. And here's where it gets, I think, just freaking wild, all right? They fired one electron at a time, and that electron still produced an interference pattern, indicating that each individual electron somehow interfered with itself, and that is a hallmark of wave-like behavior. And so, the key takeaway from this experiment and the other two is that subatomic particles like electrons exhibit both wave-like and particle-like properties depending on the conditions in which they are observed. And this duality fundamentally changed our understanding of matter and energy. And this leads us into our third objective, where we want to talk about the atomic spectrum of hydrogen. Another important experiment was the study of the emission of light by excited hydrogen atoms. When a sample of hydrogen gas receives a high-energy spark, the H2 molecules absorb energy, and then some of those bonds are broken. The resulting hydrogen atoms are excited. That means they contain excess energy, which they release by emitting light of various wavelengths to produce what is called the emission spectrum of the hydrogen atom. Now, to understand the significance of the hydrogen emission spectrum, we have to first describe the continuous spectrum that results when white light is passed through a prism. So when white light is passed through a prism, what we observe is that it contains all of the wavelengths of visible light. All right, very much like when sunlight is dispersed by raindrops, right? The rainbow produced when sunlight is dispersed by raindrops. In contrast, when the hydrogen emission spectrum in the visible region is passed through a prism, you only see a few lines, each of which correspond to discrete wavelengths. And the hydrogen emission spectrum that you see here, this is called a line spectrum. So from here, we should start to think, well, what results in an emission spectrum? And in addition, it's also important for us to equally talk about absorption spectrum. Now, in the case of absorption, hydrogen atoms in their ground state, so their lowest energy level, they're going to absorb specific wavelengths of light, which will excite the electrons to a higher energy level. This absorption process creates a spectrum featuring dark lines on a bright background, and each dark line actually represents a wavelength that is absorbed by the electrons as they move to higher energy states. Now, in contrast, the emission spectrum, which you see here and we've talked about, this occurs when these excited electrons go back down to a lower energy state, to a lower level. In that process, the electrons release energy in the form of light. The emitted light consists of wavelengths that correspond to the energy differences between the hydrogen atom's specific energy levels. In this process, it results in this line spectrum. And this is characterized by bright lines on a dark background. Each line represents a specific transition between energy levels, and it's a unique fingerprint for hydrogen. Now, the follow-up question to that is, what is the significance of the line spectrum of hydrogen? Well, it clearly indicates that only certain energies are allowed for the electron in the hydrogen atom. So in other words, the energy of the electron in the hydrogen atom is quantized. Changes in energy between discrete energy levels in hydrogen, it will produce only certain wavelengths of emitted light. So for example, a given change in energy from a high level to a low level, this is going to give a wavelength of light that can be calculated by Planck's equation. And so any sort of movement from a higher level to a lower level is going to emit different frequencies and different energies of light. In short, the discrete line spectrum of hydrogen shows that only certain energies are possible. That is, the electron energy levels are quantized. Now, in contrast, if all and any energy level were allowed, then that emission spectrum would just be continuous. But it's not, and it further confirms that energy is quantized. With that, let's move into our fourth objective on the Bohr model. In 1913, Niels Bohr introduced his model of the hydrogen atom. He suggested that an electron in a hydrogen atom moves in a circular orbit around the nucleus, and that these orbits correspond to certain fixed energy levels. The stability of these orbits contradicted classical physics, though, which would predict a collapse of the atom due to the spiraling in of the electron. Now, Bohr tried to reconcile this by adopting Planck's findings that energy is quantized, and he stipulated that electrons could only occupy certain orbits with quantized angular momentum. These orbits are going to represent stationary states with specific energy levels, and an electron transition between these orbits results in the emission or absorption of energy equivalent to the difference in energy levels, adhering to Planck's quantum concept. Now, it wasn't clear why this should be true, but with this assumption, Bohr's model gave hydrogen atom energy levels that were consistent with the hydrogen emission spectrum. Now, in mathematical terms, Bohr expressed the energy levels of the electron in the hydrogen atom as E equals minus RH over N squared. RH is Rydberg's constant for hydrogen, and this is equal to 2.178 times 10 to the minus 18 joules per electron. Now, the negative sign, it indicates that these energy levels are bound states with the zero of energy defined as the state where that electron and proton are just infinitely separated. There is no interaction between them. Now, as that principal quantum number n increases, the electron moves to a higher energy level, which are less bound to the nucleus. And remember, n is an integer. The larger the value of n, the larger the orbit radius. Now, Bohr's model, what it did was it illuminated the quantized nature of energy levels, and it provided an explanation for the spectral lines of hydrogen. But there are very much limitations to this model, and we're going to discuss them here in the next objective, so shortly. But let's talk about some of his conclusions just a little more. Bohr, he worked through this for the hydrogen atom, and so we want to talk about this in terms of defining some important terms: ground state and excited state. Now, the terms ground state and excited state, they refer to the energy levels of an electron in an atom. The ground state is the lowest energy state of an electron, and it is where it is the most stable. When an atom is in its ground state, all of its electrons are in the lowest possible energy levels. An excited state occurs when an electron within an atom absorbs energy from an external source, whether it be a photon or thermal energy, and it moves to a higher energy level. This state is less stable than the ground state, and the electron tends to return to a lower energy level, and in that process, it releases energy. Now, the transition of an electron from one energy level to another involves the absorption or emission of a photon, which is a particle of light with an energy that matches exactly the difference in energy between the two levels. And with that, I want us to repeat our definitions and understanding of absorption and emission. Remember that when an electron is in its ground state and it absorbs a photon with the right amount of energy, it will transition to a higher or an excited state. This specific energy absorption is characteristic for each element. And again, remembering what the absorption spectrum looks like up here, it results in the appearance of a dark line in the absorption spectrum at the wavelength that corresponds to the energy of the absorbed photon. As for emission, all right, you can have an excited electron that returns to a lower energy level. In that process, it emits a photon with energy that is equivalent to the energy difference between those two levels. And this emission, going back to our image here, produces bright lines on a black background. These bright lines are specific wavelengths in the emission spectrum. Now, this train of thought, it will lead us to this figure that we see right here. Here we can discuss some important series that describe the concepts we just talked about. First one we want to talk about is the Lyman series. This describes the transition of an electron from a higher energy level, an energy level greater than 1, back down to the first energy level. All right, so the Lyman series describes the transition of an electron from a higher energy level, n greater than 1, down to the first energy level, n equals 1. The photons that are emitted or absorbed during this transition, they lie in the ultraviolet region of the spectrum, so UV. Then we have the Balmer series. The Balmer series accounts for the electron transitions from higher energy levels, n greater than 2, down to the second energy level, n equals 2. This series lies within the visible spectrum, which is why the Balmer lines are actually historically significant. They were the first spectral lines of hydrogen to be observed and correlated to a model of electronic transitions. So this falls in the visible range. Then the Paskin or Paschen series, however you pronounce it, this involves transitions from higher energy levels, think n greater than 3, down to the third energy level, n equals 3. These transitions emit or absorb photons in the infrared region. Now, in addition, the energy of the emitted photons correspond to the difference in energy between the higher energy initial state and the lower energy final state that we can calculate using an equation called the Rydberg formula. This equation is essentially saying the following. The energy of the emitted photon corresponds to the difference in energy between the higher energy initial state and the lower energy final state. And it might seem strange to see an equation that has an initial minus final, where most equations usually have final minus initial, but ultimately, this equation is designed to work just like you'd expect. If an atom emits a photon, then this equation is going to give us a negative value for energy, indicating a decrease. And you can try this out yourself by plugging in values and seeing what you get. Now, with that, we can move into the fifth objective, but we will actually end the video here and we'll pick right back up in the next video. I hope that this has been helpful so far. Please let me know if you have any questions, comments, concerns down below. Other than that, good luck, happy studying, and have a beautiful day, future doctors.